Hey everybody, you know most bridges are fixed in place, duh, but some are designed to move, lifting, rotating, or tilting to let ships pass. Join me, I'm going to count down 15 of the most amazing movable bridges. Starting with number 15, the Ponjac Shabban de Muer. The Ponjac Shabban de Muer in Bordeaux, France, is the longest vertical lift bridge in Europe. It opened in 2013 and it spans the Garonne River and was named after Jacques Shabban de Muer, a former French Prime Minister and longtime mayor of Bordeaux. This modern achievement combines striking architecture with efficient technology, allowing both vehicle traffic and large maritime vessels to share the same corridor without permanent obstruction. Now, the bridge features a central span about 117 meters at 384 feet long that can be raised vertically between 4 tall pylons. When fully elevated, the central section rises 53 meters or 174 feet above water. Now, this vertical lift system was chosen over bascule or swing bridge designs due to the unique environmental demands of this river. The river serves as a key route for commercial and tourist vessels, particularly Bordeaux's cruise terminal located upriver. Now, architecturally, it does blend in with a sleek, modern design and functionality. With 4 lift towers standing 77 meters tall, they're illuminated at night with changing light schemes to reflect the tidal movements. The bridge's operations are controlled from a nearby command center with electronic systems monitoring wind speed, traffic, and water levels. And in addition to that maritime clearance, the vertical lift design also helps reduce mechanical strain over time, improving long-term durability and reducing maintenance. Overall, the Ponjac Shabban de Muer is a prime example of how modern cities can accommodate both land and river transportation in a single elegant structure. It does reflect a 21st century approach to infrastructure, efficient, sustainable, and designed for a mixed-use urban future. Number 14. Slhofberg, the Flying Drawbridge. In the city of Leeuwarden in the northern Netherlands, a uniquely engineered bridge known as the Slhofberg provides a highly efficient solution for both road traffic and water navigation. Completed in 2000 and named after the Dutch poet and writer J. Slauerhoff, this fully automatic drawbridge is unlike traditional bascule bridges in both form and motion. It uses a vertical lifting mechanism that allows the entire roadway section to rise straight up and pivot outward like a mechanical arm. The bridge operates on a pivot and a counterweight system, and it's controlled entirely by hydraulics. The movable platform, which makes up the road deck, weighs around 15 tons and is suspended in the air by a pair of vertical lifting arms. When a boat approaches along the canal, the hydraulics raise the deck straight into the air, creating enough clearance for maritime traffic. The process takes only a few seconds, making it one of the fastest operating bridges of its kind. But what sets it apart is the compact footprint and its speed. Because the bridge rises vertically and doesn't swing or lift at an angle, it requires less horizontal space. That makes it especially useful in dense urban areas. The bridge services a relatively quiet neighborhood, but its design is known worldwide due to its distinct appearance and its function. The rising motion looks like a square panel flipping upwards, giving it the nickname the Flying Drawbridge. Well, despite its small size, it handles both vehicle and pedestrian traffic and does so with minimal energy usage, thanks to its counterbalance system. The Netherlands, with its dense network of canals and its reliance on integrated water management, it's home to hundreds of movable bridges. But the Slhofberg is not the largest nor most heavily trafficked, but it is one of the most visually striking examples. It's a practical response to a very Dutch challenge, balancing high waterway usage with road mobility in compact urban areas. Number 13. The Tower Bridge. The Tower Bridge in London. It's one of the most iconic examples of movable bridges, and it's perhaps one of the most recognizable bridges in the world. Completed in 1894, it spans the River Thames near the Tower of London, and it serves as a combined bascule and suspension bridge. Its movable central sections, known as bascules, can be raised to allow river traffic to pass. That's a feature that remains operational to this day. The bridge was designed by architect Horace Jones and engineer John Wolfe Barry, and its construction took about 8 years. At the time of its completion, it was a major feat of engineering. 2 central bascules, each weighing over 1,000 tons, were originally powered by steam engines and operated using a system of counterweights and hydraulic accumulators. In 1976, the system was converted to electro-hydraulic power, but the bascule mechanism remains largely original in design. The raising of the bridge takes about 5 minutes, and it's scheduled according to river traffic timetables published well in advance. Any vessel with a mast or height over 30 feet or 9 meters can request a bridge lift free of charge, provided they give 24 hours notice. This practice continues under the Port of London Authority's guidelines, and despite its age though, Tower Bridge handles both road traffic and pedestrians, with around 40,000 crossings per day. Maintenance here is continuous and includes regular inspections, paintings, and upgrades to mechanical systems. The bridge was closed for extensive renovations in the 2000s, during which key parts of the lifting mechanism were modernized. Inside those towers is a public exhibition that includes access to the original steam engines and, of course, panoramic walkways above the river. It is a popular tourist destination, but it also remains a critical piece of London's transport infrastructure. The bridge's enduring functionality over more than a century shows the effectiveness of the bascule bridge design. It combines practical engineering with architectural presence, and it serves as a textbook case of how movable bridges can meet the demands of both waterway and road users in a major global city. Number 12. Puente de la Muer, Argentina. Located in the Puerto Madero district of Buenos Aires, Argentina, the Puente de la Muer, Spanish for the Bridge of the Woman, is a rotating pedestrian bridge known for its design and elegant mechanics. Completed in 2001 and designed by Spanish architect Santiago Calatrava, the bridge combines aesthetic ambition with practical mobility across a very busy waterway. The bridge spans a canal in the city's revitalized docklands, and it consists of a single cantilevered span that pivots horizontally to allow boats to pass. The entire structure rotates 90 degrees around a central support tower using an electric motor housed in the foundation. At 170 meters long and 6.2 meters wide, the bridge serves pedestrians and cyclists, connecting key cultural and commercial areas of Buenos Aires. The asymmetrical design features a sharply inclined mast and suspension cables that give the impression of a dancing couple, a design that does align with its name, an homage to tango culture. But despite its artistic emphasis, the bridge operates reliably. Its rotation takes less than 2 minutes, and it's executed through a turntable mechanism beneath the central pier. The rotation is performed on demand and only affects a portion of the canal's edge, making it efficient for narrow waterways in urban settings. The bridge has become one of the region's modern landmarks. Its profile stands in contrast to the surrounding post-industrial architecture, and it's often photographed as a symbol of the city's urban renewal. While relatively small in scale compared to the road bridges, it does represent a successful integration of movement and design, plus function. More than just an architectural statement, though, it plays a role in connecting foot traffic and facilitating maritime access. Number 11. The Viskaya Bridge in Spain. The Viskaya Bridge, also known locally as Puente Colgante or the Hanging Bridge, is the world's oldest transporter bridge and one of the most unique movable bridges still in daily operation. Opened in 1893, it was designed by Alberto Palacio, a disciple of Gustav Eiffel, and remains a rare surviving example of transporter bridges, where a suspended gondola carries passengers and vehicles across a river. Unlike traditional movable bridges that will lift or rotate their road deck, the Viskaya Bridge uses a fixed structure topped with a horizontal truss suspended by 4 towers, each about 45 meters high. Hanging from the upper truss is a gondola or ferry platform suspended by steel cables. This gondola moves horizontally across the river on a set of rails powered by electric motors. It takes about 90 seconds to complete a crossing and can carry up to 6 cars and several dozen passengers at a time. Now, the choice of a transporter bridge design was pretty practical. At the time of construction, there was a need for a river crossing that wouldn't obstruct the maritime traffic. By placing the crossing platform high above the river and allowing a gondola to travel underneath, the engineers achieved an uninterrupted river access and continuous land-based transport. This bridge is still operational more than 130 years after it was built, and it operates approximately every 8 minutes during the day and continues to serve as a vital commuter link, and it's a UNESCO World Heritage Site. The bridge did play a key role during the Spanish Civil War in the 1930s, suffering some damage but ultimately being preserved. Its historic significance is matched by its engineering. It represents a creative solution to the challenges of combining uninterrupted river navigation with land connectivity. Today, the bridge stands as an example of an engineering approach that was once more common in port cities around the world, but now has largely disappeared. It continues to meet modern transportation needs while preserving its historic identity. Number 10. Mystic River, Connecticut. The Mystic River Bascule Bridge, it's also known as the Mystic Drawbridge, is an example of a rolling lift bascule bridge located in the historic town of Mystic, Connecticut. It opened in 1922 and it was designed by the Strauss Bascule Bridge Company of Chicago. This bridge spans the Mystic River at a central point in the town's waterfront, carrying vehicle and pedestrian traffic. What sets it apart, though, is the rolling lift design, a subtype of bascule mechanisms. Unlike a standard hinge drawbridge that pivots upward, the Mystic River Bridge's counterweighted leaves roll backwards along a curved track as they lift. This allows the bridge deck to rise smoothly and efficiently, requiring less energy than other types of movable bridges. It uses two massive counterweights, each weighing 230 tons, to balance the bridge leaves during the lifting process. Now, the bridge lifts about 2,200 times per year, primarily during the warmer months when the boat traffic increases. It provides roughly 40 feet of clearance when raised and typically takes about 5 minutes to open and close. Mechanically, the bridge does remain close to its original form. It operates using large electric motors and a complex system of gears and trunnions housed in a machinery pit located beneath the bridge deck. Despite its age, though, the bridge remains structurally sound and fully functional. Periodic maintenance includes steel repairs, repainting, and electrical systems upgrades. The Connecticut Department of Transportation oversees the bridge's operation, and in 2022, the town celebrated the bridge's 100th anniversary with public events and historical displays. It remains a working piece of history, showing how practical engineering and historical preservation can coexist in a busy modern setting. Number 9. King's Ferry Bridge in England. The King's Ferry Bridge, located between the Isle of Sheppey and the mainland of Kent in southeastern England, is one of the United Kingdom's rare examples of a combined road and railway vertical lift bridge. Opened in 1960, it serves as both a crucial transport artery and an engineering relic that continues to function. The bridge was designed to replace an earlier swing bridge built in 1906, which itself was unable to handle the increasing road and rail traffic post-World War II. The current structure spans 1,137 feet across the Swale waterway and consists of a central vertical lift span. The mechanism that lifts it comprises two steel towers on either side of the span, housing counterweights and pulley systems. These counterweights are balanced to the weight of the central span, allowing the lift to happen with relatively low energy input. When raised, the span provides a clearance of about 80 feet or 24 meters, allowing cargo vessels and yachts to pass underneath. It takes about 2 to 3 minutes to complete a full lift cycle. Now, what makes it unique is its hybrid usage. Vertical lift bridges that serve both rail and road traffic are rare globally, and King's Ferry is one of the few remaining in full operation. Many residents work or study off-island and rely on the bridge daily, so it supports freight traffic headed to the Sheerness port, which handles containers, bulk goods, and automobiles. Though the bridge remains operational and structurally sound, the growing volume of traffic led to the construction of a second crossing, the Sheppey Crossing, in 2006. This modern fixed-span bridge handles the majority of vehicular traffic and offers 4 lanes, eliminating any delays caused by the bridge lifts. In popular culture and media, the King's Ferry Bridge occasionally appears in documentaries about railway infrastructure or transport innovation in the UK. And while it may not have the visual appeal of London's Tower Bridge or the grandeur of continental spans, it fulfills a crucial operational role. In essence, the King's Ferry Bridge represents the very specific kind of movable bridge, one not built to dazzle, but to serve. Its ability to support both rail and lift on demand, and remain operational after 6 decades, demonstrates how movable bridges are not always about spectacle. Sometimes they're just about resilience and engineering foresight. The domino effect of such infrastructure reaches into daily life, local economies, and long-term regional planning. Number 8. The Alfredan Railway Bridge in the Suez Canal, Egypt. Alfredan Railway Bridge is one of the most technically ambitious and strategically important movable bridges. Now, what makes it extraordinary is that it holds the title of the longest swing bridge in the world, with a total length of 1,100 meters or 3,600 feet, and a main swing span of 340 meters or 1,115 feet. It's on a rail-only structure built to reconnect the Egyptian mainland with the Sinai Peninsula via railway line. The bridge's size, setting, and engineering make it unique not just in the Middle East but globally. Given the Suez Canal's essential role in international shipping, the crossing over it has to be movable to prevent interference with the 24/7 flow of vessels. The original bridge at this location dates back to 1918, built by the British during World War I, as it was a temporary military supply route. In 1942, another bridge was constructed during World War II, but it too was dismantled in peacetime. The current structure, the 4th at this location, was built in 2001, incorporating lessons from previous versions. The entire operation is automated and controlled from a central tower located nearby. Opening and closing takes about 30 minutes, and the process is coordinated with the Suez Canal Authority. Now, because the Suez is among the busiest canals in the world, accommodating about 50 ships per day, this bridge operates under highly restricted schedules. It cannot be opened or closed at will. Instead, it's only used during carefully timed windows when maritime traffic is paused or rerouted. This infrequency of operation means the bridge is largely closed to rail service. In its current form, it serves primarily military and occasional cargo rail use. However, due to the severe constraints imposed by canal shipping, regular civilian or commercial use has been limited. Plans to build a parallel tunnel system and additional fixed rail bridges have been discussed in Egyptian infrastructure strategy meetings for years, but such projects are expensive and face logistical challenges. In 2015, the Egyptian government announced the construction of the new Suez Canal, a parallel waterway running beside the existing one, meant to facilitate two-way maritime traffic. And while this canal segment solved shipping delays, it further complicated the Alfredan's bridge usability. With separate canals to cross, Egypt's railway planners now face the challenge of constructing either a much longer bridge system or incorporating a tunnel beneath both waterways. So in summary, the Alfredan Railway Bridge stands as a rare feat of modern swing bridge engineering, integrating its massive scale with operational precision. While its practical role may be limited right now, its design remains an example to human ingenuity. Moving on to number 7, the Broadway Bridge, Portland, Oregon. The Broadway Bridge in Portland is one of the city's most iconic and heavily trafficked movable bridges. It's known for its distinctive roll-type bascule mechanism, a rare form of bridge engineering that combines rolling and rotating to raise the span. Opened in 1913, the bridge crosses the Willamette River and connects downtown Portland with the northeastern part of the city, serving thousands of vehicles, cyclists, and pedestrians. Now, the roll design differs from the standard bascule bridges in that it allows the bridge leaf, the movable section, not only to rotate but to also slide horizontally on a track. This combination reduces the torque required for lifting and allows a more compact counterweight arrangement. The original construction used riveted steel throughout, and in keeping with the early 20th century bridge aesthetics. The bridge measures about 1,600 feet or 492 feet in length, with the main span extending 278 feet or 85 meters. When the draw is fully open, it provides over 90 feet of vertical clearance. Over the years, the Broadway Bridge has undergone numerous upgrades to improve safety, extend its lifespan, and modernize its mechanics and electrical system. The most extensive renovation happened in the early 2000s when the city of Portland replaced the bridge deck with a lightweight fiber-reinforced polymer surface, one of the first applications of this kind of technology on a major lift bridge in the U.S. The bridge is listed on the National Register of Historic Places. That's a designation that acknowledges not just its engineering, but also its role in shaping Portland's development. Its early adoption of the roll-type mechanism, its continued service, and its successful integration into the modern cityscape make it a standout example of bridges. Today, it remains a working example to innovative engineering from the early 20th century. Its combination of form and function, blending mechanical ingenuity with civic utility, ensures that it continues to serve as both a physical and a symbolic connector across the Willamette River. Number 6. The Pont du Recouvrance in France. The Pont du Recouvrance in Brest, France, is a vertical lift bridge that stands as one of the tallest of its kind in Europe. Spanning the Pente River in the heart of the city, the bridge is both a functional piece of transportation infrastructure and a historic landmark. Originally completed in 1954 to replace the Pont National destroyed during World War II, the Pont du Recouvrance remains one of the most significant post-war engineering achievements. A vertical lift design was selected over a bascule or swing bridge due to the width of the river and the vertical clearance required by Navy vessels. The resulting structure features a central lift span 88 meters long, flanked by 4 concrete towers that span 64 meters. When the bridge is lifted, the central span rises between the towers to a height of 45 meters or 148 feet above the river, allowing ample space for even large warships and cargo vessels. For decades, it carried road traffic and pedestrian walkways, serving as a primary east-west connection in Brest. However, as part of a broader urban revitalization effort in the 2000s, the bridge was modified to carry a modern tram line, which became operational in 2012. Despite the changes, though, the bridge retained its original design integrity and continued to function with reliability. The design here is notable for its industrial aesthetic, clean concrete lines, exposed metal structures, and utilitarian proportions. These features reflect the urgency of post-war reconstruction. Brest had been heavily bombed during World War II, and this bridge became a symbol of the city's resilience. The bridge has also become a cultural fixture in Brest. The distinctive silhouette is visible from many parts of the city, and it often features in local art, photography, and celebrations. The towers are lit at night with LED lighting, highlighting the structural design and contributing to the city's nighttime skyline. It is a piece of strategic infrastructure with military, civic, and cultural importance. Its continued operation after nearly 70 years reflects both the robustness of its original design and the foresight of those who modernized it for future generations. Number 5. The Arthur Kill Vertical Lift Bridge. The Arthur Kill Vertical Lift Bridge connects Elizabeth, New Jersey to Staten Island, New York, spanning the Arthur Kill tidal strait. It is the largest vertical lift bridge dedicated exclusively to rail traffic in the U.S., and it was the longest in the world at the time of its completion in 1959. The bridge was constructed by the Baltimore and Ohio Railroad, or the B&O, in response to growing industrial demands. The decision to build a vertical lift bridge was made in order to maintain full navigational clearance for maritime vessels using the Arthur Kill, while also ensuring the stability required for constant freight operations. The bridge's central span is 558 feet long, which can be lifted vertically between two towers that rise about 215 feet above the water. When in the raised position, the bridge provides about 135 feet or 41 meters of vertical clearance, allowing ships to pass underneath with ease. The lifting mechanism relies on massive counterweights, each weighing more than 1,100 tons, suspended within the towers. These counterweights balance the weight of the deck, allowing the electric motors to raise and lower the span using relatively modest amounts of energy. The operation takes about 15 minutes and are coordinated with maritime traffic to avoid delays. During its early years, the bridge facilitated huge volumes of freight, particularly serving industrial complexes of Staten Island. However, rail traffic declined sharply in the 1980s and 90s, and industries shut down or shifted to other transportation methods. The bridge then fell into disrepair and was eventually taken out of service in 1991. For over a decade, it stood unused, raised in its open position to allow unimpeded maritime traffic. In the early 2000s, though, the Port Authority of New York and New Jersey invested heavily in revitalizing freight rail service to Staten Island. After multi-million-dollar rehabilitation efforts, which included structural upgrades, the Arthur Kill Vertical Lift Bridge was reopened in 2007. Despite its purely utilitarian appearance, though, the bridge represents a milestone in engineering. Its massive scale, long lift span, and integration into one of the busiest shipping zones in the world make it a remarkable accomplishment. It's the reliability of the bridge that's kept it relevant decades after its initial construction. Although not open to pedestrians or vehicles, the bridge does remain a striking feature of the regional landscape. The twin towers, the boxy steel structure, and bright red lift span are visible from multiple vantage points across Staten Island and the Elizabeth waterfront. It may not be a household name, but for those working in transportation, logistics, and heavy engineering, it is considered one of the great movable bridges of the modern era. Number 4. Gateshead Millennium Bridge, Newcastle, UK. The Gateshead Millennium Bridge is one of the most distinctive movable bridges in the world. It's located in northeast England. This pedestrian and cyclist-only bridge spans the River Tyne, connecting the city of Newcastle upon Tyne on the north bank with Gateshead on the south. Unlike traditional drawbridges, bascule bridges, or even vertical lifts, this bridge features a unique tilting mechanism that's earned it the nickname the Winking Eye Bridge. When a vessel needs to pass beneath, the entire structure rotates backwards on its axis like a giant blinking eye, lifting the pedestrian and cycle deck while lowering the arch to provide vertical clearance. The motion is graceful, efficient, and completely unlike any other bridge's operation, making it an iconic example of modern engineering and urban design. The bridge was conceived in the late 1990s as part of a broader regeneration effort. The objective was to create a landmark pedestrian connection between the Baltic Center for Contemporary Art and the Newcastle quayside. The local council and the UK Millennium Commission launched a design competition, and the winning submission came from the engineering firm Gifford & Partners in collaboration with Wilkinson Eyre Architects. Construction began in 1999 and was completed by 2001, the bridge officially opening to the public in September of 2001. The total cost of the project was about £22 million, funded largely by the Millennium Commission. When activated, the bridge pivots on large bearings and slowly rotates backwards to provide a vertical clearance of 25 meters or 82 feet at mid-span, enough for most boats and river cruises. Structurally, the bridge is made of steel and weighs over 850 tons. It spans 126 meters or 413 feet across the river and measures 8 meters or 26 feet wide. The entire lifting process takes about 4.5 minutes and is nearly silent, which does add to the surreal quality of watching a bridge rotate like a giant blinking eye across the river. What's perhaps most surprising about this bridge is its reliability. Despite the unconventional design, the tilt mechanism has proven extremely robust over more than 2 decades of service. It's rarely experienced any operational failures, and the city's investment in high-quality components and preventative maintenance has ensured continued performance. In 2021, for the bridge's 20th anniversary, it underwent major inspections and minor refurbishment, including replacing some of the control components. In broader terms, though, the bridge represents a different philosophy of infrastructure. Rather than focusing solely on vehicle throughput or maximizing cargo capacity, the bridge prioritizes human-scale connectivity. It is a bridge that moves, but also a bridge that moves people in another sense. It transforms how they relate to their city, to the river, and to each other. Ultimately, the bridge is an example of how innovation, when matched with intention and execution, can create something that lasts. It's a statement of pride and practicality, a rare combination in the world of movable infrastructure, and in other cities around the world, they face the challenge of adding pedestrian mobility without disrupting maritime traffic. The Gateshead design offers not just an inspiration, but a working blueprint. Number 3. The Scherzer Rolling Lift Bridge in Chicago. So the town of Chicago is famous for many things: the skyline, deep dish pizza, and its historic role in the evolution of American industry. But to engineers and transportation historians, one of its best features lies not in its skyscrapers or the cuisine, but in the bridges. More than any other American city, Chicago has become synonymous with movable bridges, and among these, the Scherzer Rolling Lift Bridge is uniquely ingenious. Invented in the late 19th century, this lift mechanism found its ultimate expression in the bridges spanning the Chicago River, where they remain in operation over a century later. They're not only functional, but artifacts of American ingenuity. The story begins with a man named William Donald Scherzer, a brilliant mechanical engineer from Chicago who sought to improve the limitations of existing bascule bridges. Traditional bridges like this used massive counterweights to pivot and lift one or both leaves or sections of a bridge upwards, creating a gap for passing boats. These designs, while effective, required large pits and heavy machinery to accommodate the movement of massive weights. Scherzer's key innovation was to design a bridge that rolled backward on a curved track as it lifted, sort of like a rocking chair in motion instead of rotating on a fixed hinge. This not only reduced the stress on the structure and the machinery, but it allowed for a quicker, more stable operation. Maybe the most iconic example is the Wells Street Bridge, built in 1922, which combines a double-deck Scherzer rolling lift design. The lower deck carries trains and pedestrians, while the upper deck handles automobile traffic. It's one of the very few such bridges in the world to lift both decks simultaneously. Each leaf weighs over 1,000 tons, and the bridge opens over 3,000 times a year, making it one of the busiest movable bridges in the U.S. Chicago currently has more than 40 of these movable bridges, many of which use the Scherzer system, or a modified version of it. Operating one of these lift bridges is both an art and a science. Bridge tenders undergo specialized training to control the motor systems, monitor weight balance, and coordinate with boat traffic. Despite their age, many of these bridges can still complete a full open and close cycle in under 10 minutes. The bridges, of course, are inspected regularly, with teams checking for wear and tear on the rolling tracks, lubrication of the trunnions, and the calibration of the counterweights. But in the end, the Scherzer Rolling Lift Bridge represents a unique intersection of history and endurance. Invented in the 1890s, it still serves millions of people today, and not just in Chicago. His design is a reminder that great engineering doesn't just solve immediate problems, it shapes the identity of cities, creates lasting cultural symbols, and continues to operate long after its inventor is passed. More than a century after they first rolled open, Chicago's Scherzer bridges remains a marvel of kinetic architecture, deserving not only of preservation, but of celebration. Number 2. The Katvik Bridge in Hamburg, Germany. The Katvik Bridge is one of the most impressive examples of a modern vertical lift bridge. It occupies a crucial role in the infrastructure of one of Europe's busiest ports. Located in the southern area of the Elbe River, the bridge was originally completed in 1973 and designed to accommodate both rail and road traffic across a key waterway. Over 4 decades, it held the title of the tallest vertical lift bridge in the world. Then, in 2020, the new railway-exclusive bridge, known as the new Katvik rail bridge, was opened alongside the original to enhance its capacity, reduce wait times, and allow more efficient separation of cargo types. Now, the original bridge was designed to lift its central span vertically between 2 massive steel towers. The lift span is 100 meters long, or 328 feet, and the clearance when raised is 53 meters, or 174 feet. Before its construction, the only alternative for crossing this segment was the long detour or waiting for a barge. The bridge not only improved its connectivity for industrial and commercial traffic, but also helped streamline rail operations, linking Hamburg's port terminals with the national trans-European freight networks. It operates using a counterweight-based lifting system housed in the twin towers, each about 70 meters or 230 feet tall. When the bridge is raised, massive counterweights, each weighing more than 600 tons, descend within the towers. One key feature of the design is the precision of its locking mechanisms and damping systems, which ensure that the bridge level is secure for rail and vehicular traffic when it's closed. From a structural perspective, both bridges make extensive use of steel box girders, trusses, and pre-stressed elements to balance the strength and weight efficiency. The lifting spans are designed to remain rigid during motion, and shock absorbers and mechanical locks prevent unwanted movement across the bridge once it's in the down position. Over the years, both bridges have become iconic in their own right, not because of their aesthetics or tourist appeal, but because of what they represent: efficiency, precision, and the evolving needs of one of the world's most dynamic seaports. It's very German. Their towering structures, visible from miles away, mark a zone of continuous activity and movement, where ships, trains, trucks, and cranes operate in tightly choreographed coordination. Despite being utilitarian, the bridges have garnered attention from the global engineering community. The Muer Bridge in particular was the recipient of several design and construction awards in Germany for its use of modular construction. Advanced surveying equipment and laser alignment tools were used to ensure the bridge's lift span would dock perfectly with the approached rails, critical for high-speed freight operations. These bridges are not just flashy monuments or tourist attractions. They're workhorses, critical, adaptive, and highly optimized structures that perform an essential function. As global trade intensifies and the need for resilient logistics systems grows, bridges like these will only become more vital, and in Hamburg, they already stand as proof that innovation, when applied with discipline and foresight, can keep an entire city and continent moving. Number 1. The Cape Cod Canal Railroad Bridge, Massachusetts. Spanning the Cape Cod Canal in Massachusetts, the Cape Cod Canal Railroad Bridge is one of the most visually commanding and sophisticated vertical lift bridges in the U.S. Officially opened in 1935, it was once the longest vertical lift bridge in the world and remains one of the most significant railway bridges in North America. Now, what makes it remarkable is not just the scale, but the consistent performance over nearly a century. Built during the Great Depression as part of a major infrastructure effort by the U.S. Army Corps of Engineers, the bridge was designed to accommodate the growing importance of both maritime and rail traffic. The vertical lift design allows the central span, measuring 544 feet or 166 meters, to rise 135 feet or 41 meters above the canal. When lowered, the deck provides a direct rail connection for freight and limited passenger service between the mainland and Cape Cod, while the twin towers that support the lifting machinery soar more than 271 feet or 83 meters up into the sky. Now, the canal itself is 17.5-mile wide artificial waterway operated by the U.S. Army Corps of Engineers. Completed in 1914 and widened in the 20s and 30s, the canal dramatically shortens maritime routes by eliminating the need for vessels to navigate between the often dangerous outer coastline of Cape Cod. It was built by the Phoenix Bridge Company, an American bridge company, and it cost about $1.5 million at the time. That was a significant sum during the Depression. Construction began in 1933 and was completed in just over 2 years. That was a rapid timeline considering the complexity of the project. The lift span, constructed using a truss design, it offers both strength and lightweight efficiency, and the trusses form a deep framework of interconnected steel beams arranged in a series of triangular patterns. When raised, the bridge provides more than enough vertical clearance for almost any ship that travels through the canal, including military vessels, cruise ships, and large commercial cargo carriers. The bridge's operation, though, is not without its challenges. Given its age, parts occasionally need to be fabricated custom due to the unavailability of off-the-shelf replacements. Weather, particularly the corrosive effects of sea air and the potential for ice accumulation in winter, also pose long-term threats to the structural elements. And in addition to the day-to-day role, the bridge is sometimes used in training exercises for emergency response teams, naval logistics, and infrastructure resilience assessments. Because of its strategic location near a navigational choke point, the bridge is also included in federal continuity of operations plans. That underscores its relevance not only for local transportation, but for national preparedness. The Cape Cod Canal Railroad Bridge is a rare combination of historic engineering, modern reliability, and significance. While it lacks the flash of contemporary cable-stayed bridges or the architectural flourish of urban pedestrian spans, it more than compensates with longevity, utility, and dignity. For Cape Cod and for Massachusetts, the bridge is more than just steel and motors. It is motion, connection, and continuity in physical form.